Hi, my name is Bradley Chambers. This is my thesis presentation on methane and oxygen from energy efficient, low temperature in situ resource utilization on Mars. I'm working under Dr. Shri and with our postdoc, Dr. Shahed. For this presentation, in situ resource utilization is abbreviated as ISRU. Let's first talk about the Martian conditions. We know from orbiters and rovers that there are perchloric salts that depress the freezing point of water to allow for the existence of liquid phase and solid phase brine water cycle on Mars. Additionally, the atmosphere is 96% CO2, which presents the opportunity to utilize efficient low temperature carbon dioxide electrolyzers on the surface of Mars. NASA's current goal is to synthesize the rocket oxidizer needed to return a crew from the surface of Mars. They are currently using a system called MOXIE, which is a high temperature solid oxide electrolyzer on the Perseverance rover to synthesize elemental oxygen by reducing the atmospheric CO2. The limitations of their system we seek to address in my electrolyzer is that there is carbon coking from the Bois-Dard reaction at high temperatures, high temperature energy penalties, and it also doesn't make the second component in rocket propellant, methane. My first aim was to model the performance of the electrolyzer in Martian conditions through utilizing thermodynamic parameters at Martian ambient temperatures. This green 3D graph here on the left is the first part of the model, where Dr. Shahed and I plotted the electromotive force or the thermodynamic energy required for the reaction to be carried out across the Martian diurnal temperature range at varying reaction extents in equilibrium. The thermodynamics used to create the 3D plot are entropy, enthalpy, Gibbs free energy, and linear fit lines generated for the specific heat of the products and the reactants. Up at the right here, you can see a 2D figure of my electrolyzer cell where the atmospheric CO2 is entering at the cathode, and then the Martian brine feedstock is entering at the anode. That is to be split into oxygen and H+ ions. There's a cation exchange membrane to transport the H+ ions to the cathode where the electroreduction of CO2 into methane occurs. The next part of our model was to incorporate experimentally gathered performances of a copper cathode and a ruthenium oxide anode in Martian temperatures. This was in order to get a validated performance of my electrolyzer in Martian conditions. This was then scaled up to a theoretical 10-cell stack at 20 volts, which generated approximately a power normalized production of 0.31 grams per watt per day of methane and 3.54 grams per watt per day of oxygen. MOXIE only generates 0.8 grams per watt per day. Another benefit of my electrolyzer is that it is a platform to synthesize other key products on Mars like carbon monoxide, formaldehyde, methanol, ethylene, and ethanol. In conclusion, my Martian ISRU electrolyzer is theoretically 4.4 times more efficient at synthesizing oxygen than MOXIE, but requires the additional feedstock of Martian brine. Additionally, my Martian ISRU electrolyzer creates methane for the second component of rocket propellant and can synthesize other key products for humanity to one day traverse our solar system.